Hey everyone. I'm going to be talking about problem 1D/2F from round 736, and I'm only going to be talking about the easy version because that's the version that I solved in contest. So this is 1D/2F easy version of round 736. So as always, read the problem first, think about it by yourself for a little bit, and then if you're still stuck, then read the tutorial or like watch this video, and hopefully I can help you understand the problem a little bit better. So what makes this problem easy is that all the coordinates are even, and I'm going to explain to you why this is really important, or like why this makes a problem easier to solve. But before I do that, I'm going to have to introduce you to two different formulas. The first formula that I'm going to quickly go over is Shoelace theorem. And just as a disclaimer, like these formulas that I'm about to talk about, that doesn't necessarily mean that you absolutely have to know them to solve this problem. I'm just explaining the way that I approached this problem in order to solve it. And the way that I solve this problem is through using these theorems. So the first one that I use is called Shoelace theorem. So like specifically for triangles, because that's the only version that really matters in here. So what Shoelace theorem for triangles states is that if the vertices are located at points like x1, y1, x2, y2, and x2 and x3, y3, if those are where the vertices are located, then the area of this triangle will be equal to 1/2 times x1, y2 plus x2, y3 plus x3, y1 minus what is it? I think it's minus is it minus x1? Hold on. Okay, no, it's minus x1, y3 minus x3, y2 minus x2, y1. Like this is what the area of like a triangle is equal to. And so this is like the first theorem over here. And I'm actually just going to explain really quickly why this is important. So we know that the problem is basically asking how many triangles exist such that the three vertices of these triangles fall among the n given lattice points, and there exists an odd number of distinct points in this triangle, and also this triangle has to have an integer area, which is also important. So in other words, a triangle can only be valid if this quantity over here is an integer. Well, the easy version states that all of these coordinates are even, and because all of these coordinates are even, that guarantees that the area of this triangle is an integer. And here's why. All of these terms, like x1, like x2, x3, and also y1, y2, y3 are all even. In other words, they're all divisible by 2. So if all these numbers are divisible by 2, this number over here has to be divisible by 4. It's like it has to be like, I'm just gonna write mod 4 is equal to 0. And then this quantity over here also has to be divisible by 4. So does this one, so does this one, and this one. Since all 6 of these like products are divisible by 4, adding these numbers and then like subtracting some numbers means that this entire like quantity in the brackets is also divisible by 4. So if we take some number that's divisible by 4 and then we divide it by 2, this guarantees that we have an integer number that's divisible by 2. So using the Shoelace theorem and the fact that all these coordinate points are even, not only can we guarantee that any triangle we pick will have an integer area, but this integer area will also be a multiple of 2. So in other words, we can guarantee, like in the easy version, it is always guaranteed that the area is an integer, and divisible by and even. In other words, like divisible by 2, like mod 2 is equal to 0. And the fact that the area is always an even number is also important for the next theorem that we're about to use. And this theorem is called Pick's theorem. And I know that's a really weird name, like haha, Pokemon, Pixelmon, I don't know, like Minecraft, like Minecraft pick, you know? Okay, I don't know what I'm saying. So Pick's theorem. What does this theorem state? According to a reputable source called Wikipedia, Pick's theorem states that A is equal to I plus B over 2 minus 1, where this is the area of a given triangle. This is equal to the number of interior lattice points. Interior lattice points. And then this is and then B is equal to the number of like perimeter lattice points. It's like the number of lattice points that are on the perimeter of like some number. So like I'm just gonna say perimeter lattice points. And then 1 is, okay, if you don't know what number 1 is, then I'm sorry. But anyway, why is this theorem useful? Well, we know that in our, like, based on what we've deduced from the Shoelace theorem, we know that this quantity A is always going to be an even number. Also, in the problem statement, it says that in order for a triangle to be like counted, it has to have an integer area, which we know it always has, but it also has to have an odd number of enclosed cows strictly inside of this triangle, where a cow is located at an integer coordinate. Well, it turns out that that's literally just what an interior lattice point is. So the number of cows in some triangle will just be equal to I, and we want I to be odd. So what this means is that A is always going to be an even number. It's like, I'll just say A is always going to be an even number, and I will always be an odd number. And then this is like plus some B over 2, and it's like minus an odd number, because 1 is an odd number. So what this means is that if we look at the parity like of this equation, this implies that B over 2 has to be an even number. And this further implies that B mod 4 has to be equal to 0. So the number of like lattice points on this triangle's perimeter has to be divisible by 4. And so basically we can think about it like this. When a number is divisible by 4, like when a number is divisible, when we want to check whether a number is divisible by 4, we can think of it like this. Since all these lattice points are even, if we just divide all of these lattice points by 2, it's like if the input is x and y, but we read the point in as x over 2, y over 2, this condition, then instead we can basically just check a condition where b mod 2 is equal to 0. In other words, instead of checking whether b is a multiple of 4, all we have to do is check whether b is even. And this transformation helps us out a lot, because we can do this. And this is basically what allows us to get to like this final solution, I guess. So let's think of it like this. Let's just assume that we have just like a set of endpoints that like looks like this in the plane. I don't really care what their specific coordinates are. I'm just using this to kind of showcase how to implement this problem. So let's just say that we know that this is like what the points look like after we divide all the coordinates by 2. We want to choose a set of like 3 points such that the number of lattice points on these edges is an even number. And so, in other words, like if this hits like 2 lattice points on here, aside from the endpoints. So it hits like 1 lattice point on here, then it hits 6 lattice points in total. And because 6 is an even number, we want to count this triangle towards the answer. But clearly, we can't just count every single choice of triangle because that's n cubed and n is 6,000, and that would definitely TLE. So how can we implement this in n squared? Well, that's what I'm about to explain to you right now. Poggers. God, I'm disgusting. Okay, anyway, let's just assume that we can notice that any triangle can be defined like this. If we pick like a center node, so like let's just say like this node, like not the node, but this point over here is a center, then we can like connect all of these other points on the center. So I can just like connect it's like we can just like visualize these as lines, and like each line has like a specific number of lattice points that it intersects with. And so if we want to choose, so now we can think about it like this. How can we count the number of triangles? Yeah, how can we count the number of triangles we can form such that one of these triangles' vertices is the center node? And what's useful about this is that this is equivalent to basically saying we want to pick 2 lines such that if we like, for example, we picked this line and this line over here, the sum of all of the lattice points between on this line, and on this like new line is going to be equal to an even number. So how do we do this? Well, it's really easy. Like if we call this center point C, and like all these arbitrary points, like just other arbitrary points, it's really easy to count how many to just like manually count how many lattice points are on the line from some point I to the center point C. Specifically, the formula will look something like the GCD of the x coordinate of I minus the x coordinate of C, and like between the y coordinate and minus the y coordinate, like something like this, like absolute value, whatever. And so technically you actually want to add 1 if we looked at line segment like by itself, but because we want to consider the sum of all of the sum of like 3 line segments together, if we just use a standard formula where it's like +1, each endpoint is going to be counted twice. And so in order to make sure we only count every endpoint once, we just ignore the +1. So this tells us how many lattice points are on some line, but we only care about whether we have an odd or an even number of lattice points. So we really only care about the GCD of like the value over here. We only care about it mod 2. In other words, we only care about whether it's odd or even. So that's like one important thing. And then another important thing, and like kind of the trickier step, is how do we determine, like, how can we count the number of pairs such that this like third edge over here, like the edge that's not connected, that doesn't have the center node as an endpoint, how do we tell like whether this edge is like even or odd, and how can we maintain this? Well, okay, let's think of it like this. I'm going to suggest, or no, not suggest, okay, how do I say this? Okay, so like I explained just now, if we have some center node C, then we can figure out the parity of the number of lattice points on each of these like outgoing lines. So let's just say, for example, this is odd, this is even, this is even, this is odd, and this is even. Yeah, it's like odd, even, odd, even, whatever. And so let's say we want to compare, let's just say we want to compare like these 2 lines over here. So we have like any 3 points over here. We know that there's an even number of lattice points in here, and there's an odd number of lattice points in here. So this means that we have to have an odd number of lattice points on this third line. How do we know whether or not there's an odd number of lattice points in here? Well, we can use a GCD formula like we used earlier. So I'm going to assume that this is point A, and I'm going to assume that this is point B, just like for simplicity. And we know that we care about this quantity over here, the GCD of like AX minus BX and AY minus BY. So And this number, and we only care about this number like mod 2. So let's ask ourselves, when is this quantity even? Already think about it? Okay, well, here's the thing. If we only care about whether the GCD is odd or even, we can essentially mod these coordinates by 2. So we only care about whether AX, BX, AY, and BI are odd or even respectively. We don't really care about their actual value because we only care about the GCD like mod 2 at the very end. So what this means is that we want to make, in order for this GCD to be an even number, this quantity over here has to be an even number, and this quantity over here has to be an even number as well. The only time that both quantities will be even numbers is when when the parities of AX and BX are the same, and the parities of AY and BY are also the same. So, for example, if AX has odd parity, BX also has to have odd parity. And if AY has even parity, then BY has to have even parity. And that's the only way we can guarantee that GCD, or like a number of lattice points on this line from point A to point B, is an even number. But wait a minute, in this specific case over here, we don't want this to be an even number, we want it to be an odd number, because an even number plus 2 odd numbers will be an even number. So how do we count like this odd number case? Well, this only matters depending on the parity of like these coordinate points over here. So in other words, we can maintain a map where for every line that we draw, like from the center to like some point X, or X is kind of a misleading term. I'll just say like point I. We care about 3 different things. We care about the parity of the edge from point C to point I. And so let's just say this is like A. We also care about the parity of the X coordinate of I. Let's just call it X. And we also care about the parity of the Y coordinate of I, which in this case we'll just call Y. And we'll keep like a count of all of these values. And so this is useful because now instead of having to deal with like n different points in like n different cases, there's only a total of 2 cubed, like 8 different categories every line can fall under. And because there's only 8 different categories that fall under, we can just like consider which category can we pair with like another category such that they form a valid triangle. So I'm going to just go over like one case. All of these, there's like several cases that you could handle, and all of them are very similar with each other. So I'm not going to go too in depth with it. But pretty much what we do over here is that let's just say, for example, we have like some line that's defined as even, odd, right? In other words, the distance from a center that we care about to this current point has an even number of lattice points. The X coordinate of this point I is an even number, and the Y coordinate of this lattice point is an odd number. So let's say the second line that we paired up with is the second line that we paired up with, let's say this number over here is 1. Then this implies that, like, if this is like a center node C, let's say this is point A and this is point B. Point A and then point B. Point B over here. So we know that in this case, this is going to be an even number, and the coordinates of A is basically even and odd. Well, we know that if the line from C to B is an odd number, then we know that the line from A to B has to be an odd number in order for this triangle to be valid. And the only time that A and B will give an odd number is when B is not equal to E or O. So in other words, B can either be 0, 0. B can also be 1, 0. Like I'm talking about like the last 2 numbers. Or it can be 1 and 1. Like if B falls under any of these 3 categories, we compare it with this point A. And because we maintain like a counts of all of these numbers, we can just like multiply them together and like do some like arithmetic and like counting to figure out how many choices we can do like this. And so this is just like one case. It's also possible that this first like number over here is even. So in other words, if we choose some node or like some edge A that goes like from the center to A, if this is even and this number is even over here, then this number over here has to be even. So for example, if the number points from the center to B is 0 or like even, then we know that the number of points from A to B has to be an even number. And the only time that this can be an even number is when they're equal, B is equal to like the same state as A. So it's only 0 and 1. And the third like case we have to handle is when the edge from C to A and the edge from C to B, or not the edge, the line, they both give an odd number of lattice points. Like this gives an odd number, this gives an odd number. Then we know that the line from point A to point B has to give an even number of points. And so we just replace this first number with 1. And then we can just like calculate how many pairs exist like this. Like using, again, some like counting and like multiplication. So I know like that last part I explained might not be super clear. And I'll put my implementation down in the description because I think it's going to be a lot easier to understand what I'm trying to explain if you just look at my code for this problem. And also my code is kind of, my code is honestly kind of messy for this part. It's definitely possible to implement this in a much cleaner way using bit masks or something like that. But it doesn't really matter too much because it's just a matter of like how can you maintain these counts and how can you like account for every formula like in a specific way. But yeah, this is how you do the easy subtask of problem D from round 736, division 1. I hope this was helpful to you. And if it wasn't, then that's sad. But see you next time.